Hello and welcome. Today we have come up with the second part of Cauchy-Schwarz inequality. As you know that in the first part we have practiced some problems based on CS inequality. If you have not watched the part 1, we recommend you to watch it first. The link is in the description. In this second part, our main goal is to prove the CS inequality. As you know, here at Nidhyan Education, we don't believe in dumping the solution or proof directly before you. We gradually unfold the problems by figuring out some hidden hints in them. So the proof of CS inequality is not an exception. We shall unravel the proof by using the good makes of wishful thinking and some work behind the curtain. In the first part, we have seen another version of CS inequality that we call T2's lemma. Today we shall see one more version that is popularly known as triangle inequality. And at the end, we shall solve an excellent problem from ISI 2009. So needless to say, stay tuned till the end. Let's start with a short recap. This is the statement of Cauchy-Schwarz inequality that we have already exploited in the first part. Now we are going to prove it. So the first question is, how can we prove it? This is not an easy question. It is not immediately clear where to start. In fact, there is no obvious evidence to figure out a way which may lead us to the result. So what should we do now? When there is no short way, it is a good idea to play with some smaller cases with the hope that we may get some breakthrough, or at least we may get some evidence for the starting point. So let's try to prove the CS inequality for two pairs of real numbers. We take some reversible steps and eventually we reach the statement which says the square of some real number is non-negative. That is obviously true. And since all the steps were reversible, so it proves the CS inequality for two pairs of real numbers. Let's give one more shot for three pairs of real numbers. Again, we follow the same strategy of taking reversible steps. Indeed, the calculations are painful, but this pain is worth to bear. Finally, we reach some statement which says that the sum of three squares is non-negative. Again, it is a true statement. Thus, we prove the CS inequality for three pairs of real numbers as well. But our goal of doing these two exercises is to find a clue for the general proof of CS inequality. Did we get any clue? The answer is yes. We notice that the squares are playing some deep role in CS inequality. Also, we notice that the condition for equality is nicely related with the squares. So we have a hope that we can prove CS inequality by considering suitable function involving the sum of squares. Let's consider fx is equal to a1x minus b1 whole square plus a2x minus b2 whole square up to anx minus bn whole square. Notice that fx is a quadratic polynomial and fx can be 0 if and only if x is equal to a1 over b1 is equal to a2 over b2 up to an over bn. Otherwise, fx is positive. So we are going to express these two conditions mathematically. But for this, we require one standard result. We express the result in this lemma. Let me read out the statement for you. If ax square plus bx plus c is greater than or equal to 0 for all real x, notice that for all real x, then the discriminant is less than or equal to 0 and the leading coefficient is positive. Try to prove this lemma yourself. But here is a word of caution. Don't confuse this result with its converse. Its converse is also true, but proving this result is not as easy as proving its converse. Now all is set to prove CS inequality. Let's get started. So this is the statement which we want to prove. Modulus of a1 b1 plus a2 b2 up to an bn is less than or equal to square root of a1 square up to an square into square root of b1 square up to bn square. We quickly notice that if all ai's or all bi's are 0, we get 0 less than or equal to 0, which is obviously true. So the result holds in this case. Also, we notice that if any of AI or any of BI is 0, we can omit it because it will not play any role in the result. So it is sufficient to prove the result by considering non-zero AIs and BIs. We start with the function what we assumed just before. As we have already noticed that fx is a non-negative function, and since fx is non-negative, so by using the lemma given before, its discriminant must be non-positive. Pay your attention here, this is the key step. We have noticed that fx is non-negative, so by using the lemma given before, its discriminant must be non-positive. And now we follow the routine steps and we reach the CS inequality. That's it. This completes the proof. We understand that it is not easy to assimilate the proof in the first attempt. So if you are learning CS inequality first time, we recommend you to pause the video and read the steps carefully. If you have any doubt, don't hesitate to ask in the comment section. We did really work hard to prove this result. We had no perceptible way to reach here. So we investigated smaller cases and we gambled on a function fx which consisted the sum of squares. In this way, with some wishful thinking, a bit of luck and a lot of courage, we proved the result. You can take it as a template to prove results in mathematics. Wishful thinking, luck and courage are keywords to go in unknown and find out something unforgettable. Let's move on. The result we just proved can be thought of as a stronger form of CS inequality because the result holds even if we remove the modulus sign from LHS. But this result is weaker than the previous one because it is implied from the previous one. Also notice that the equality holds in the weaker form if and only if the ratios of AIs and BIs are equal, but the common value of the ratio should be non-negative. Notice here, the common value this time should be non-negative. We strongly recommend you to give some time to absorb it. Let's move on to another version of CS inequality, which is popularly known as triangle inequality. This is the statement of triangle inequality. For some real AIs and BIs, we have a square root of a1 plus b1 whole square plus a2 plus b2 whole square up to an plus bn whole square is less than or equal to square root of a1 square plus a2 square up to an square plus square root of b1 square plus b2 square up to bn square. And the equality holds if and only if AI is equal to kbi for some non-negative real k. We can prove it by taking reversible steps. And we take some reversible steps and eventually we reach the CS inequality. This is how we show that triangle inequality is nothing but the another version of CS inequality. Here is the one question for you guys. Can you justify the name of the inequality? We call it triangle inequality. But where is the triangle? Let us know in the comment section. As you know, we write super amazing books and many of you are getting benefited from our books. We have given CS inequality in detail in our Algebra Volume 2. Check out the links of our books in the description. Finally, it is the time to take problems. Here is the first problem. For positive x, y and z, we are asked to prove square root of x square plus y square plus z square plus square root of 1 over x square plus 1 over y square plus 1 over z square is greater than or equal to 2 square root of 3. Where should we start from? Is this inequality suggesting any approach? The answer is yes. The inequality contains the sum of two square roots. It is a strong hint to use triangle inequality. Let's do it. We get this inequality. Now what? RHS is not even close to what we want. What should we do next? Yes, you are right. We should attempt to minimize RHS. But how can we minimize the RHS? Notice that in the RHS, we are getting the sum of reciprocals. AMGM inequality is an ideal tool in such situations. So by using AMGM inequality, we minimize the RHS and hence we get the desired result. This completes the solution. It was a good problem based on triangle inequality. Once we initially hit the idea of using triangle inequality, the rest of the work was not very difficult. We are giving you a couple of problems for practice. Let us know your work in the comment section. Let's discuss one last problem, and it is going to be a fantastic one. Find the values of x and y for which x square plus y square takes the minimum value, where x plus 5 whole square plus y minus 12 whole square is equal to 14. Unlike the last problem, this problem is not giving any strong hint to use the Cauchy-Schwarz inequality. So it is natural to ask yourself, why is this problem a good candidate for CS inequality? The answer to this question becomes clear when we expand the squares and we apply the CS inequality to get the upper bound of 10x minus 24y. So this gives us a hope that we can get an inequality in square root of x square plus y square, which might land us to the minimum value of x square plus y square. Let's execute this idea. We simply expand the squares and we isolate the term of 2 into 12y minus 5x, and we get an upper bound of 12y minus 5x by using CS inequality. And this allows us to set up an inequality in square root of x square plus y square. Read these steps very carefully. If you want, you can pause the video. These are the crucial steps. Now let's assume alpha and beta are the roots of LHS. So we factorize it in this way. But we have to make sure that alpha and beta are distinct positive real numbers. We observe that the discriminant alpha plus beta and alpha into beta are positive. So this ensures that alpha and beta are distinct positive real numbers. Thus, we get the lower and upper bound of x square plus y square. Now the question is for which values of x and y, x square plus y square attains its extremum values. To figure out those x and y, we have to find such x and y for which the equality holds at the first inequality when we applied the CS inequality first time. And the equality holds in this inequality when we have y over 12 is equal to x over minus 5. Let's take these two ratios equal to k and we get x is equal to negative 5k and y is equal to 12k. Now to find the value of k, we plug in these values of x and y in the given relation. Thus we get two values of k, which was expected because for 1k we get minimum x square plus y square. And obviously for other k we get maximum x square plus y square. But we have to figure out which k gives which extremum, because don't forget that we are interested in finding such x and y for which x square plus y square is minimum. So to figure out the required k, we find x square plus y square is equal to 169k square. And for a smaller k, 169k square is smaller. So naturally, the smaller k gives minimum x square plus y square. And in this way, we get the required x and y, for which the x square plus y square is minimum. This completes the solution. Indeed, this problem was not easy. We had a mild hint to use the CS inequality. But as we have already noticed that the good mix of wishful thinking, luck and courage land us to the destination. And fortunately, this happened in this problem as well. Interestingly, we have a completely different approach to tackle this problem. We can give beautiful geometric interpretation of this problem. We notice that the given equation represents a circle with center negative 5, 12 and the radius is square root of 14. We take an arbitrary point P, x, y lies on the circle. Notice that square root of x square plus y square is nothing but the distance between x, y and 0, 0. So the requirement of finding x and y for minimum x square plus y square is equivalent to find the coordinate of the point on the circle which is at the minimum distance from the origin. Try yourself to find that point and let us know your ideas in the comment section. That's it in this video. Hopefully you enjoyed it. If you find this video helpful, hit the like button and share your experience in the comment section. Next week we shall discuss an amazing technique which allows us to tackle the inequalities in the triangles. This technique is extremely efficient to tackle the inequalities in the triangles, and we call it Ravi's substitution, and we are sure you are going to love it. So stay tuned with us. Thanks for watching this video. See you next week.